Thank you. So I want to talk today about some work we have been doing on trying to make AI and machine learning systems more accountable. So what I mean by accountability here is that we want to subject these systems, the objects of study here are machine learning systems, put them under the microscope and try to understand why they're behaving the way they are. So you can think of that as a form of explanation that might explain specific predictions coming out of these AI systems or predictions about groups of individuals. Then building on those on those explanations, we would like to identify certain blind spots that might exist in these systems, like systemic weaknesses perhaps, diagnose them, and then go on to fix those issues so that the overall goals of the system are improved. Now, this is very analogous to how natural scientists and social scientists study objects in the physical world. My wife is a biologist, and she experiments often with mice. And we have social scientists who study other kinds of animals, like people. And in a sense, we are trying to develop the same kind of methods grounded in causal analysis and apply them to these special beasts that are machine learning systems. So I'm not going to spend a lot of time on motivation. The whole morning session and the previous talks have set up this topic area very well. John Launchbury's talk in particular talked about the third wave, which is essentially what I'm talking about as well. I'll give you snippets of some technical ideas that we have been developing here at Carnegie Mellon. So explanations are important in many different settings. We would like the machine learning systems inside of our autonomous vehicles to be well understood so that we are sure that they don't crash into objects they shouldn't be crashing into. In security, monitoring is extensively makes use of machine learning systems for intrusion detection, for example. And there, if you have a good sense of where the blind spots are, we can improve the performance of these systems in the presence of adversarial attacks. The area in which much of my own work has focused has to do with the use of data analytics over personal information. So you can think of systems like Google's advertising system or Bing's search advertising. Facebook has similar mechanisms. And these kinds of machine learning systems are increasingly being used for credit analytics in education. We heard from Emma earlier in the morning, as well as in healthcare. And the unfettered use of machine learning in these areas pose a threat to privacy and fairness. And that is one specific application domain in which accountability is important. And I'll use that to motivate the technical development. So the grand challenge here of accountable AI is, from my perspective, to develop theories and tools that can account for behaviors of AI and machine learning systems. And what I mean by account for here is provide explanations, explain behaviors, use that to diagnose systematic weaknesses in the system, and then go on to institute corrective measures that will address those weaknesses. And a key set of ideas here that is beginning to emerge is the importance of causality in this exercise in realizing this vision. And so I'll talk, much of what I'll talk about today may be construed as reflecting this vision of causal accountability. So let me give you a concrete example to motivate the kinds of problems that I'm interested in. This is based on a study that we did of the Google online advertising ecosystem last year. We essentially did a randomized controlled experiment on the Google online advertising ecosystem. We had 500 simulated users who were male and another 500 who were identical, except that their gender was set to be female. And then they visited job-related websites as a way to signal to the ad ecosystem that they were interested in jobs. And then we measured the distribution of ads that were served to the two groups and found a statistically significant difference. Not only that, we found a specific job-related ad which had this title of 200K plus jobs, where 1,800 impressions of that ad was served to the male group and only about 300 to the female group. So there was a significant difference, a bias, if you will, in how this ecosystem was treating our simulated users based on their gender. And since this was a randomized controlled experiment with simulated users, this was not just an observational effect, it was a causal effect. So gender really caused this difference. Similar observations have been made in several other studies. Kate Crawford's recent New York Times op-ed article has a good summary of several other studies. I'll point out one from this ProPublica report from Julia Angwin, which showed similar racial bias in the way that sentencing scoring systems are working based on where race has a significant effect on how likely the system is to predict that a specific individual is likely to recommit crime. So these are some examples that motivate why we may want to get some explanations. So in the Google study, we studied it from the outside. We have no idea why this particular outcome was achieved, but ideally, we would like to be able to study these systems from the inside to be able to generate explanations. So the problem of explanations is very broad, but let me focus on one specific instance of it for which we have some technical results. And that is this question of feature influence. So the specific question we are asking is how much causal influence do various inputs or features have on a classifier's decision about individuals or groups? Now this might be interesting from a fairness standpoint because if gender or race or some proxy for it has a high influence on the decisions, because that might be suggestive of a bias that may be unfair. So let me give you a concrete example. So imagine this individual with these demographic features who was denied credit. Loan application was denied. And we might wonder which of all of these features had high influence in this decision. So if, for example, race had a high influence, that might be concerning, or maybe the country of origin. Those might reveal some bias in the system. We would like to give explanations that say something like this, that the main reason for the denial was the occupation had the most influence, education had the second most negative influence, and capital gain actually was quite a positive factor. Were it not for these negative factors, this person would have ended up getting the loan. So that's the kind of explanation I'd like to shoot for, sort of teasing apart the causal influence of individual features on these decisions. So one challenge in arriving at such a definition is that input features are often correlated. So for example, consider this classifier that's making a decision about credit. It uses only income. The features that go in include age and income. Now if age were used to make this decision, that would be an unfair bias. But income, the use of income, let's say, is kosher, since it's a credit decision. But if you were to just measure the correlation or some association measure between this input feature and the output, then since income, let's say, is positively correlated with age, age will also end up being correlated with the decision. So just using a correlation or associational measure is not a very good measure of influence because it doesn't tease apart the influence of these individual features. Instead, we are going to draw on this idea of causal intervention, where the idea is that in order to measure the influence of a feature, we are going to keep the other features fixed and then sample that feature from its prior distribution independently of the other features. So in essence, we are breaking the correlation between age and income and then measuring how much the output changes. So continuing with this example, if we are to keep the income fixed and sample age from its prior distribution, then we will see that that has no effect on the output. That means that the output does not change at all, even when you keep changing the age. That means, according to our notion of influence, that age has no influence on the decision. In contrast, if you keep age fixed and keep sampling income from the prior distribution of income, then the decision keeps changing. And we can quantitatively measure how much that influence is. So that's the first idea. Now that by itself does not solve the entire problem, because sometimes single inputs might have insignificant influence. So here's an example where the decision of the classifier now depends both on the age and the income. So if you were to only change one feature at a time, then you won't see any influence. It'll say that neither of the features have any influence at all. So the next idea would be to do the causal influence measurement over a set of inputs instead of just a single input, and that would say that this set is influential. But that by itself is not good enough, because not all features in the set are equally important. So we haven't teased apart the relative importance of the features. So that takes us to the idea of marginal influence, where we look at the influence of the set with and without the feature age and measure the difference. And that's the marginal influence contribution of age to this set. But age is part of many different sets. So just looking at one specific set that it contributes to does not give us a good measure of how its overall influence is. So that's where we build on ideas from cooperative game theory, which gives us measures or power indices that aggregate marginal causal influence. And I won't get into the math, but the idea here is, think of the US presidential election, and there is the power of California versus Pennsylvania depends not just on how many votes each state brings, but also the prior. Some states tend to always be blue, some are always red, and then there are the Pennsylvanias and the Floridas and the Ohios that win the elections. And so there's a specific Shapley value that ends up being a specific power index called the Shapley value that ends up being quite appropriate for our setting. So that's how we measure the aggregate influence of features. So returning to my running example, for this kind of explanation, our Shapley value measure will say that capital gain here has a very high positive influence. Notice that occupation has a very high negative influence, and then education also has a negative influence. And so this more abstract picture here on the right is an abstraction of this more detailed quantitative measure of feature influence. Now this by itself is just a starting point for where we are hoping to go with this kind of explanations. As you might suspect, that explanation does not work very well at all for deep neural nets, because the initial features are just these pixels, and saying that one pixel is very influential will not give us any meaningful human interpretable explanation. If the intermediate features end up being human interpretable, then this method could work. More broadly, the way we are thinking about this problem is that the goal would be to extract simpler programs that explain predictions of the complex machine learning system in local neighborhoods. So the idea here is that you can't expect to abstract a deep learning net with a simple decision tree and expect that it'll work equally well all over the space. But in local neighborhoods, suppose we are trying to explain a specific prediction, or a prediction for a group of people in a certain neighborhood, maybe in some part of a manifold, to steal some of the terminology from John Stock, then we might be able to get these kinds of explanations, and we are beginning to work towards this goal. So that's it. Let me stop here with the summary that there's a very interesting research area now developing on accountable AI, where the goal is to develop theories and tools to account for behaviors of AI and machine learning systems. And this includes explanations for behaviors, diagnosis of systemic weaknesses, instituting corrective measures. And so far, we have been largely doing experimentations with systems. So you can think of this as a clever form of black box testing. But we are beginning to also starting to look inside the black boxes and develop starting to think of these problems as program abstraction problems. And that's where the connection to probabilistic programming that Jeanette mentioned in her talk is beginning to emerge. Thank you very much.